All right, looks like we got about 60 people signed in. It's about time to start, so I'm ready to go. All right, good morning, good afternoon, and good evening, everyone. This is the Measurement and Analysis for Protocols Research Group meeting in concert with IETF112. My name is Dave Blanca, and Miria Kuliwind, the co-chair, is also on. The IRTF follows IETF intellectual property rights. If you're going to talk about anything here that your company or your organization has applied for a patent or has been granted patent, you're required to disclose that in a timely fashion. See the details in the RFCs and documents linked here if that's appropriate for you. The note, privacy and code of conduct. This meeting is being recorded. It's in the public. The information you present here will be available publicly. The privacy policy is linked there. We also expect you to abide by the code of conduct, be respectful to other people. Harassment is not tolerated. If you find instances of this, there's contact information to the ombudsman there, but just please be courteous in your participation in our meeting.
Yeah, let me actually add a few words because I think this is really important for our community. And so just pointing people at these code of conduct and the anti-harassment policy is a serious point and not only something we skip through. I think this is also very important for us in the IRTF because especially in this group, we have a lot of newcomers, and so we should be very welcoming and open, I think. And that doesn't mean that you cannot criticize anything, but if you criticize something or if you provide feedback, provide it in a constructive way and be friendly and help people to get to know the IETF. I mean, consider this for this session. I don't think we had any problems in the past, but also consider this for all the other sessions you're participating in, for all activities around the IETF and the IRTF, also for the chat, not only when you speak up on the mailing list or in the session. And also, please speak up if you see behavior that is not appropriate. You don't have to speak up in public, and of course, it's always a subjective judgment, but it does help to approach those people and tell the people that you personally had the feeling that something was not okay, so we can all improve and make this a better environment. And I go to the next slide.
Thanks, Miria. So the goals of the IRTF is to support and present research work. It is not the standards organization that the IETF is, even though we are co-located and use some of the same procedures. And there's more information about that at the link provided here. So Administrivia, the charter for MAPRG, which has been running more than 5 years now, is available at the link there. Please subscribe to the mailing list if you want to hear about upcoming MAPRG things, but also related topics. We regularly get advertisements for calls for participation or contributions in other workshops and symposia and conferences that are about measurement of internet things. And you'll see today that we sometimes host those in the MAPRG meeting as well. Today's slides are available. Go ahead.
Go ahead, sorry.
Today's slides are at the link there. You can find them in the agenda, search for MAPRG.
And I just see that I missed the Meet Echo link, but you're all here, so that's great.
Yeah, I saw that too, and I was like, well, we're showing the slides to people in Meet Echo, so I thought the one place it didn't need to be was right there right now. But all right, next slide. The Jabber is, by the way, linked to the same chat you see in Meet Echo. A small announcement, the IAB workshop on analyzing IETF data is coming up. Miria is one of the organizers of that. And that's November 29th to December 2. The call and the selection process has already occurred, but we're letting you know that that's there. For instance, to give you an idea of work that will be presented there that's peripheral and related, but not in MAPRG. For instance, Stephen McQuiston and his co-authors did a work on characterizing the IETF through the lens of RFC deployment. So you can imagine it has a lot to do with the things that you might be interested in, especially if you're working on protocols and the standardization, but it's not about measurement of the protocol itself, so we're not hosting it here. On a similar note, SIGCOM 2021 happened in August of this year. There's also some work that you might be interested in that again wouldn't be in MAPRG because it's not about Utu had a nice piece of work there called Insights from Operating on an IP exchange provider that is about running a global network of fiber optic links in parallel with the internet used, for instance, for global roaming for mobile. So you can see why that wouldn't be here per se, but we wanted to let you know that there's work in SIGCOMM that's related to the work here that you might want to go and visit. Next slide, Miriam.
Yeah, maybe just also the authors of those documents, feel free to use a MAPRG mailing list to announce this work and make people aware.
Absolutely.
Yeah, and also I recommend everybody to check out the last IMC that was just last week. There's a lot of interesting papers, and we have a bunch of interesting papers today from IMC as well.
Okay, so the agenda for today, first up we'll have, so a number of these pieces of work are from IMC, and it's a subset that samples across the kind of things that MAPRG usually does. First up, we'll have Giovanni Mora talk about Suname and this problem with the DNS system and work that they carried on to adapt the protocol to not have this problem. So an actual engineering effort there. Next up, we'll have Nicholas Kuhn bringing some new work to us and some early work about VPN performance over satellite communications, and each of these will have 10 to 15 minutes, and we'll have time for questions between. Then we'll switch to IOTLS from Talha Paracha, and that's a piece of work from IMC, obviously about how the protocols are actually being used in operation, in this case with IoT. And then we'll round out the meeting with Kyle McMillan bringing us their work on measuring the performance and network utilization of popular video conferencing application. What I can tell you, I'm happy about this meeting today because we've just got 4 things, and if I stop talking, we should have approximately 5 minutes of comments for each of them. So let's get underway. Miria, can you stop sharing that slide? I guess I should call and say, is there any questions or comments at this point? I don't see anyone in the queue. So we can bring up the first presentation. Giovanni, can you put yourself in the queue? All right, there you go. And do you plan 10 or 15 minutes for your talk?
It's perfect. You folks hear me well?
Yep.
All right. So thanks, Dave. Thanks, Miriam. Good morning, evening, or afternoon, depending on where you are. So I'm going to present here this work we did together with folks at Internet New Zealand and USC. This was a paper that we presented last week at IMC. So if you want to get a full paper, here's the link. We actually identify some issues with current RFCs with regards DNS, and we wrote a new draft, which the link is also here. So we're looking for feedback. I sent the draft to the DNS op list last Monday. If you're interested, please have a look and provide some feedback on the list. So let's get started with the name. We all know that the DNS is one the core services on the internet. And you know that because when it breaks, people do notice. And there was this infamous Mirai.net attack against Dyn, a major DNS provider that provide DNS services for Netflix, Spotify, and so forth. And when Dyn went partially down in the US, it made to the front page of the the New York Times. You can see here a picture of the zones in the West were like partially affected on this picture here. So it's a big deal. And when we talk about DNS, there are 2 major types of servers. There is if you have a client in this figure here, the client wants to go, let's say, to a domain like wikipedia.org. The client sends a DNS query to it's configured with this local resolver, which is configured with, and the resolver does sort of the heavy lifting. The resolver is just like trying to find where this information it's located in terms of DNS to map the the domain name to IP address, and this information is fetched ultimately from these authoritative servers, as you can see here. And once this information is fetched, the resolver responds to the client can go happily to Wikipedia. And Suname affects specifically traffic to authoritative servers is the resolvers that would kind of overwhelm authoritative servers. And this all happened when we were working together in a paper for IMC 2019 or 20, and there is 2020 actually, and this is traffic that arrives at the authoritative servers of New Zealand. And the folks there were getting, an average of 750 million daily queries, so all the .NZ queries that come to them. But one day to the other, they saw this 50% traffic surge in the traffic. And if you're an operator, you don't like such surprises. And that got them concerned, obviously. And when they start to dig into the data, they saw the two domains in their zone basically had no queries before, very little daily queries, and out of a suddenly they start to get like more than 100 million queries each. And they wonder if that was a denial of service attack. And if that were, why it was actually targeting domain names were not popular at all. That does not make any sense. But it turned out that there was a misconfiguration in this particular two domains. Domain A was misconfigured with a loop, which we call cyclic dependency. Domain A, when you try to resolve that, would actually point to domain B, but domain B in turn would point back to domain A, which would create a loop. And that situation, some resolvers, when they find loops for some clients, they start to loop and send in non-stop queries. And the effect of that overwhelms authoritative servers. And this particular event on New Zealand, that was not a major issue for them, but it could have been. So as I said, a cyclic dependency is an error, it's a configuration error, and one domain points to, let's say, cat.nl points to nz.dog, ns.dog.nz, but dog.nz would point back to ns.cat.nl, and then you create a loop. And 1536 describe it. This paper published 2004, they covered that in more details. The issue with this domain is that it can never be resolved. And what it did in this paper in particular is to show how this vulnerability can actually be weaponized. We also provide a tool for the DNS authoritative server operators to get rid of these loops in their zones, because many times you're not aware that it exists in their zones. So we provide a tool that's open source tool, PsychoHunter, they can download and scan their zones, and also identify what's missing in current RFCs. And we help them also fixing bugs. We carry out responsible disclosure. We did notify first the vendors and the specific groups, and then later carry out the public disclosure. And that led to Google and Cisco public DNS fixing their servers, we were very happy about that. But the real threat in this case of tsunami is that its weaponization is that two domain names in .nz that had zero basic little traffic caused a 50% total traffic surge. And the threat is that the diversity would hold many domains, and it would reconfigure many domains with these loops, and then trigger recursive resolvers queries from a botnet. That could potentially, bring down DNS providers. So we got very concerned about that. And in practice, the root causes of these loops are twofold. The first one is that resolvers themselves, this infinite number one there, the resolvers, when they see this sort of loops in the DNS configurations, they would simply start looping. We found old versions of Windows resolvers doing just that. So that's one of the cases. But the other case is that the clients themselves would start looping. They would stop sending queries nonstop, and that would cause resolvers also to loop. And the ultimate effect is on the targets here. These authoritative servers would see the surge in traffic. The solutions we'll cover later. And, people know that loops in DNS are not no problem, but isn't that solved already? But it turned out that RFC 1034 was the first DNS RFC. It's very vague about loops. They say it resolves just should bound amount of work to avoid infinite loops. But that would only protect resolvers from overwhelming, for the first part of the loop here, the infinite one. It was just forbid resolvers from looping indefinitely and overwhelming authoritative name servers, but does not protect any amplification from clients. So the clients would send queries nonstop to resolvers, and then resolvers in turn would loop themselves for every new query that arrives. So that does not protect in this case. 1035 recommends to set counters in this case to forbid again resolvers from looping, to prevent resolvers from looping. But again, does not provide any protection if clients or forwarders are actually looping themselves. 1536 says that loops can occur. Again, does not protect from looping clients. So the solution we actually provide in this paper is that this is not really covering any standards at the moment. The resolvers should actually do negative caching, should detect those cycles, and put in their cache. So every new client query can be like responded from cache and does not make it to the authoritative servers. And that minimizes the both causes of looping here. And that's where our draft comes from here on the DNS hub. And we also, in the paper, not only investigate what happened to New Zealand, but also we carry out a bunch of control experiments in the wild with using RIPE Atlas and other vantage points to that. So the most basic experiment we did, we configured RIPE Atlas 10,000 probes to send one query only per probe to their local resolvers. We wanted really to determine if we could get that, if one probe would send one query, if that would be enough to start looping. And it's kind of the lower bound. So we did that, and in Atlas, one Atlas probe may be configured with multiple resolvers, but what we collected, it's the traffic arriving at authoritative servers. And this is the figure you see here. On the top figure, you see sort of a spike. In the y-axis, we see the number of queries that arrive. The first spike there you see after 2 o'clock is when the normal traffic arrives at the resolvers. We see like more than 150,000 queries. But after that, there's no more queries from Atlas, but we're still getting queries at our authoritative servers for hours and hours and hours. And it only stopped when you turn off the experiment. And what happened, if you look in the graph below, it's that a portion of the resolvers, you see like on the y-axis here and on the graph below, the number of resolvers doing that. In this particular experiment, 574 actually looped, and they came from 34 autonomous systems, including Google and Cisco. And the paper have way more complex scenarios, and it gets worse if you make longer cycles. You can make 3-fold cycles, so it gets worse, and we have different vantage points, so it's a widespread. So that's the first thing we did in this paper. But the second thing we're interested is not only understand the phenomena, but also prevent it. So we wrote this tool, Cycle Hunter, which you can download here. Here's the link. It just gets your own file, gets all the NS records you have in it. That's where the authoritative servers are defined. Try to resolve them. If they fail, they try to find if they're cyclical or not, and then you have an output. And what we did, we ran Cycle Hunter. And by the way, thanks for all folks that contributed to the tool later after disclosure. We ran Cycle Hunter against multiple zones, 184 million domains, and we found that only 44 and 1,500 domain names were affected by that. And we believe it's like human error, because if you have this sort of thing, your domain is not resolvable. Then if you're a real legitimate user of your domain, you're not interested in that. But the malicious actor could just do differently and try to weaponize this. And so that's the prevention part. And then we came to the fixing bugs part. We carry out responsible disclosure. And we started in December last year to do that. And we ended up in May this year with the public disclosure. We talked first to Google, and then with a bunch of private groups that we had contacts, and including DNS ORAC, which was the biggest, ORAC 34 was the biggest group that we disclosed. And then we did calls like Google and others, and public DNS and Cisco also to fix. And we actually confirmed the Google fixes public DNS because we ran measurements before they fixed, and we repeat the same measurement using RIPE Atlas after. And you see here that before, in this particular scenario, it's also in the paper, we would get more than 4 million queries in our authoritative servers, but after that, we would get like fewer than 200,000. So we can really confirm that the Google fixed, and we see that. They fixed that by deploying negative caching too. And after we came forward with the disclosure at the ORAC 35, I think it was like 5 or minimum months and a half after we started the process of disclosing this, some operators came forward to us and they said, "Hey, your folks are not the only ones. We saw that ourselves too." And one European-based CCTOD, they were kind enough to share this graph with us. And you see here, when the graph around 17 hours started to grow, it's when 2 domains in their zone were also misconfigured, and their total traffic, increased like 10 times because of 2 domain names. So each color here shows a different authoritative name server for that EU-based CCTLD operator. So that's a big deal. And you'll see a sharp drop later on around 11 a.m. the day after when they fixed that manually. So we're not the only ones seeing that. In other tools, they also came forward during the work presentations. So that's the third part of this, the third contribution. And the conclusions is that NS loops are no problem on DNS. They have been specified since, they have been talked about since the original DNS specification. And we showed we must address it now. Current standards, current RFCs do not cover them. And that's why we propose this new draft. And what to do if you're an operator, you can run Cycle Hunter. If you run your own authoritative servers, try to find those loops in your zone. And if you're a developer of resolvers, we recommend just do what's in the draft, like negative caching of loops. And with that, I think I open to questions.
We have 2 people in the queue, and we've got a couple of minutes for their questions or comments. So first, let's take Jonathan Hoyland.
Hi, Jonathan Hoyland, Cloudflare. I'm interested. Have you seen groot or Groot by the Microsoft research people? They also do cycle hunting in DNS, and I was wondering if your tool is different, the same, solves the same problem.
I haven't seen that one. No, I have not seen. If you could share a link, I could have a look at that and talk. Yeah, well, I'm not aware of the tool, but thanks for sharing.
All right, thanks, Jonathan. Up next, we have Daniel Gilmore. Daniel, are you there? Okay, Daniel, you're at the top of the queue, but I'm not hearing you. Do you want to put your question in the chat and overlay it?
Oh, I think Daniel just wrote a question there.
I see him in the chat saying I'm trying. Yeah. Oh, now we can hear you. Go ahead.
I was just hoping you could say a little bit more about looping clients, not about looping recursors. What sort of clients were looping and what caused that?
So our vantage point was like we use Right Atlas and they query whatever the resolvers they had, but we also collect traffic and authoritative servers. But there's a lot of things that can come in between both of them. What we could find specifically, it's down in the paper, but like 2 versions of it. An old version of Power DNS from 2014 was looping. An old version of Microsoft DNS Server from 2008 was looping. We know that the clients that Google, which was the major responsible for the traffic in all the experiments we did, Google Public DNS did not loop. So the only we worked with the operators on that. So the only reason that this could be happening is the client from Google downstream, before the fix, they would be sending queries one after the other, and every query would trigger, let's say, 10 new queries to our authoritative name servers. But I don't know which clients were looping. I haven't looked specifically into that because my vantage points didn't allow me to see that, unfortunately. But at least 2 resolvers we could confirm that were old versions, they were looping. And I think there's also, does that answer your question?
I think let's assume that it does. I think there's a little bit of audio trouble there and we're at time. Thanks so much, Giovanni, for bringing that work to us. Super cool. I especially like the Cycle Hunter tool so people can see if they have the problem.
Yep. Thanks.
All right, so up next we have Nicholas. Nicholas, can you put yourself in the queue to share your slides? There you go. All right. There you go. Take it away, Nicholas. You've got 10 minutes.
Okay. Hello, everyone. So my name is Nicholas, and I'm presenting this work on behalf of a colleague of mine from Vcas. This study came because we are all, with all the pandemic that occurred, we are all using VPNs, and we have measurements showing that when you use a VPN solution and you have a SATCOM access, things can be very bad. So we wanted to do some work on and wide experiments on trying to find what is the best VPN solutions for different SATCOM accesses, and we have an archive paper showing lots of results. So as I said, we have all been working from home recently. Also, enterprises networks need to interconnect their for their different components, and this comes with increased security needs, and VPNs are usually deployed in these schemes. So I guess lots of us know what VPNs are, but the devil is in the details, and there are lots of different solutions on here. So we have been testing WireGuard, that is an IPsec solution, but also comparing it with OpenVPN on top of UDP and TCP. Dave told me that everyone is not always aware of what we do in SATCOM system, but we are not the only ones. We usually deploy TCP proxy. So basically, we have two components intercepting the triple handshake messages from TCP to have, in the end, 3 different TCP connections. We do not do that because we like to break the end-to-end principle. We do that because it has a lot of interest, and it is to answer to the specificities of the satellite links. In short, we have issues in connection initialization. We can have lots of specifically tuned initial windows in TCP PEP. Sometimes the end-to-end buffers are not in adequation with the very high BDP that we have on satellite systems. So we can have custom buffers. Also, splitting the reliability in 3 subsystems helps a lot. Loss recovery is split in 3 segments and not really end-to-end on with a very large RTT. And last but not least, when you know your system, you know the congestion status of it, and then you can actually very quickly increase the rate at which you transmit data, and so you have very homemade congestion controls that are possible in these components. Also, we do that because basically here is just a basic example on showing the page loading time without with different initial windows of TCP and the PEP, and we can see that with TCP proxies, even if we just split the connection in 3, we can have the page loading time. That being said, if we look at an let's say an enterprise network and using a satellite network, we have end-to-end the server and the PC. We may have a POP, a satellite gateway, satellite terminal, and an access box. The PEP can either be in or out of the VPN tunnel. And basically, we have seen deployments where lots of configurations are possible. So I can put my PEP within my VPN tunnel, out of my VPN tunnel. I can have lots of VPN solutions. So I can sometimes choose my congestion control, sometimes I cannot. So basically, that is the main rationale of this study. We have tested it over lots of configurations and to emulate SATCOM systems, which are or geo-based or so geosynchronous systems or LEO. We have sometimes, usually on geo systems, you have no losses. That being said, sometimes when you rent a SATCOM access, you may end up having losses. You don't know whether there are transmission losses, congestion losses, but you can measure lots of losses on the system. And then we have tested Cubic without high-rate slow starts and BBRV2. We have tested various initial congestion windows, and there are 3 different VPN solutions. And basically, the results for the case where we don't have any losses. So basically here I show the transfer time of 30 megabytes. And I will just point to different results. Basically, we have measured that when we use OpenVPN TCP and there is a PEP within the tunnel, we have very bad performances. We guess this is because we have some sort of a TCP in TCP issue, and that end up with even BBRv2 exhibiting a downloading time of up to 40 seconds. In this configuration, when we use just so the PEP in position B, so the green circle, so the PEP is outside of the VPN tunnel, and the VPN WireGuard is just an IPsec tunneling. That end up providing the best performances. Anyway, a VPN on UDP and without PEP, and basically the orange circles, we have lots of cases where we have very fair and good performances. In summary, I will have summary of the results later on. When we have losses, things are getting very as we could have expected. Basically, Cubic is very sensitive to losses on the network, while BBRv2 is not. BBRv2 ends up providing very good performances in terms of downloading time, and using it helps a lot in these cases. When we cannot use BBRv2 and we have to stick with Cubic, we can see that it is better to actually face the TCP in TCP problem, but have a proxy and VPN solution based on TCP, so that the proxy can somehow help. And so what we have measured in our short technical report is that using WireGuard is very interesting, and basically we have more or less the same performances with Cubic and BBRv2 when we don't have losses. When we have losses in the systems and that you don't manage, actually activating BBRv2 helps a lot. When you cannot turn on BBRv2, we have measured that the damages can be reduced when you use an OpenVPN TCP. Also, we wanted to mention that in this short technical study, we have emulated the losses on the satellite network. Sometimes when losses are on the local network, the PEP can help much more, because the recovery process is not occurring on the large delay path. And so basically, we have to admit that in this case that we have considered the PEP cannot really help the loss recovery process, but that is what we sometimes face in deployments where we actually cannot guarantee a loss-free SATCOM system. So we have recently published an archive paper and send a link to the list. And basically, on top of what we have shown here in the paper, we have also mentioned the conclusions we had when we tried to introduce congestion and when BBRv2 is not known, to see if there are any fairness issues. And in a nutshell, we don't have much fairness issues with BBRv2 in our experiments. So thank you all for listening, and thank you very much for MAPRG to give me the opportunity to present these results.
Hi, Nicholas. This is Dave. I wanted to relay a couple of questions, basic questions that maybe I should have interrupted you for. Can you go back to your slide with the results? The questions were just about, were these numbers total times to completion for the 30 megabit,
yes.
30 megabyte transfer? Okay, so
yes.
It's time to completion instead of some latency measure. Okay. Yeah, that was that. There's a little more discussion in the chat that you might want to check on afterwards to see.
Okay.
And anyone else with a question or comment for Nicholas? Okay, Tommy Pauly's in. We'll take Tommy's, and then we'll switch to the next presentation. So Tommy, go ahead. We can see you.
Yeah, great. Yeah, thank you so much for sharing this. Definitely interesting to see your results. One thing I'd love to see more work on, you know, if you're able to do more experiments with different types of configurations, is, you know, what can happen if, rather than using VPN and TCP proxies here, we could look at using quick-based proxies. So within Mask working group, we're using quick-based proxies, and those are able to send both reliable and unreliable data. I've been working on a project at Apple to use multi-hop quick proxies for our service called Private Relay, which is kind of like a VPN, but it's using these proxies. So I think it'd be interesting to try to see, rather than having to choose between, okay, I'm doing a TCP solution here with a PEP or a UDP solution with a PEP. If we have an ecosystem of quick proxies, could we maybe get the best of both worlds across the no loss and loss scenarios?
To be honest, we are very interested in deploying Mask-like proxies in these kind of systems, and because we didn't have running code for that, we used what was available, and we think that sometimes when we use the OpenVPN UDP, somehow, even if it doesn't include congestion control that Mask proxy would have, we can still have some trend of the results we could observe. But then, indeed, we are very interested in going further. I think it's very important for this kind of systems to look at Mask proxies and what is possible. We are.
All right. Thanks, Tommy and Nicholas. We're going to spin up the next presentation. Thanks again for joining us. All right. We can see you, Taha.
And now I should be able to see my screen. Okay.
Yep. There you go. I'll let you know in 10 minutes.
That sounds good. Okay, so hello everyone. I'm Talha. I'm a PhD student at Northeastern University. This work is about TLS usage in IoT devices and was published at IMC last week. It's done in joint collaboration with Daniel, Narceo, and Dave. So as many of us know, Internet of Things devices such as smart TVs and voice assistants are very popular and are expected to become ubiquitous. Invasive nature of these devices raises significant privacy implications. For example, some of these privacy issues in the past have been found in baby monitors, voice assistants, and even biomedical devices. In addition, compromises in device security can also lead to severe outcomes. For example, in the past, there have been internet outages, credentials leaks, and even vehicle hijacks. One of the ways to improve IoT privacy and security is to protect the network communications from IoT devices. Prior research shows that IoT manufacturers mainly rely on TLS to do so. Now, TLS is the de facto web security protocol that provides confidentiality, authenticity, and data integrity to network connections. Nicholas, I just want to briefly say there that your mic is on, in case you forgot. Okay, but to use TLS properly, our client needs to use secure protocol version and features. It needs to properly validate certificate chains, and it needs to adopt new features as the protocol evolves over time. Now, TLS usage has been studied rigorously in various platforms such as web browsers and mobile operating systems, but little is known about TLS usage in IoT devices. Hence, the main objective behind our work was to study how effectively IoT devices use TLS. However, there were a couple of challenges that we needed to circumvent first. For example, IoT devices provide limited ways to trigger traffic. In order to interact with the devices, one typically needs to plug them with a power supply and manually interact with their functionality. And second, there are limited vantage points that shed light on TLS on a traffic that is TLS traffic that is specific to IoT devices. Here's how we mitigate these challenges. First, we build on insight by prior works that devices generate significant network traffic when they are powered on. We automate device reboots with the help of smart plugs, and hence we have a way to generate traffic whenever we need for our experiment. And second, we complement these controlled experiments with uncontrolled ones that span a long period of time and enable us to study longitudinal trends. We conduct these experiments in the IoT lab at our school. We focus on the 40 TLS supporting IoT devices across a wide range of categories. We also recruit more than 30 participants to interact with these devices in the lab through an IRB-approved user study. As you may notice, our lab is designed like a studio apartment, and our participants were told that they can use any of the devices as they please. And with this setup, we obtained 2 years of longitudinal data from 2018 to 2020. I'll now share some of the key results and will then talk about one result in more detail. So the first question that we asked in the study was if these devices securely established TLS connections. On the positive side, what we found was that most devices were using TLS 1.2 and none of the devices were using insecure cipher suites. But on the negative side, we also found that very few devices upgraded to TLS 1.3 or modern cipher suites over time. The second question that we asked was if these devices properly validate TLS certificates. We found that 11 devices were vulnerable to TLS interception attacks. Our manual analysis revealed that many of these devices were sending potentially sensitive data. We have reported these vulnerabilities to all device manufacturers. We also found that devices do not appear to update their TLS root stores, and I'll talk about this result in more detail in a bit. And finally, we also asked if these devices share TLS libraries with other clients. Using a technique named TLS fingerprinting, we were able to show that devices and applications from the same vendor likely share TLS libraries. In the paper, we talk about more details about the positive and negative implications of this finding. So I'll now talk about TLS root stores in more detail. To understand what these root stores are, let's consider an example, Dls Handshake. Here, our device initiates a connection with a web server. There are many steps in the handshake. The one to remember for this talk is that at some point during the handshake, the server will send a certificate chain. The certificate chain contains a certificate authority, which in this case is DigiCert. These certificate authorities vouch for the authenticity of the server. In order for this handshake to succeed, the device must trust this certificate. More specifically, the name as well as the signature of this certificate authority must already be in the trusted root store of the device. If the device does trust the certificate, it can continue with the handshake and may mark it as a success. These root certificate authorities have the power to compromise authenticity of all connections that a device makes. Hence, it is essential to know what root certificates are trusted by IoT devices. Other platforms, such as web browsers and mobile operating systems, publish the list of root certificates that they trust and regularly update them over time. For example, here a root certificate is being removed from Mozilla Root Store because of administrative reasons. But here, the removal of this root store is due to negligence and misbehavior on behalf of the certificate authority. Inspection of root stores in IoT devices is difficult due to their black box nature. I will now share our technique. I will now show how to use completely black box measurements to try to infer root stores of IoT devices. Let's take a look at the TLS handshake again. But this time, we intercept the handshake and send a certificate chain that contains a certificate authority that is unknown to the client in terms of both name as well as signature. If the device is properly doing certificate validation, it must reject this certificate and mark this handshake as a failure. The device can also choose to share the reason of failure through a TLS alert, which in this case is unknown CA. Let's compare this with another scenario where we also intercept the handshake, but this time we send a certificate whose name is known to be trusted to the client, but whose signature does not match the signature of the certificate that is present in the device. In this case, the handshake must fail as well. So we can see that in both of these cases, the handshake fails, but the reason of failure in both cases is different. And that in one case, the reason is that a certificate is unknown, while in the other case, the reason is the failure of a signature. These two different reasons can lead to the transmission of different TLS alerts. If an IoT device behaves in such a way, we can reliably infer the presence of a given root certificate in its store. And to explore all root certificates that a device has, we can simply repeat this methodology with the names of all publicly known root certificates. Our technique of root stores exploration worked for 8 of the 24 devices we could test. In order to get a list of root certificates for whose inclusion we could check, we extracted historical root certificate data from various platforms. Using this data, we generated 2 sets of certificates. One commonly trusted certificates are the ones that are available in latest versions of all platforms. And second, deprecated certificates are the certificates that were once a part of one or more of these platforms, but have since been removed over time. We first check for the inclusion of commonly trusted root certificates. Our results reveal that most of these certificates are present in IoT devices. This is good news because it shows that IoT devices, web browsers, and operating systems likely trust a similar set of root certificates. We then check for the inclusion of deprecated root certificates. Ideally, none of our devices should trust any of these certificates, but our results reveal that most of these devices trust some of these certificates. Devices such as Google Home Mini trust a fewer percentage of these certificates, while some others such as LG TV and Invoke trust a percentage that's quite high. The likely reason for this is that devices either do not update their Tls root stores, or they do not update them at a required frequency. In order to explore more of the security implications of trusting deprecated root certificates, we manually analyzed the certificates that were still trusted by these devices. To our surprise, we found that all these devices trusted at least one certificate that has not just been deprecated, but also explicitly distrusted by either Firefox or Chrome. Based on this analysis, we argue that Tls root stores can be considered as the weakest link of security in IoT devices. To conclude, our study reveals a mix of both good and bad news about TLS usage in IoT devices. Unlike the perception in the community, we do not believe TLS usage in IoT devices is completely broken. Rather, we think it suffers from some of the same issues that existed in other platforms when they had just started their reliance on TLS. Please feel free to read our paper for more details, and I'm happy to share that we also have released the Dls Handshake data and some software from our research. Thanks, and I'm ready to take questions now.
Thanks a lot, Taha. Right on time, perfect. First, I want to refer you to people like that you're doing this work, and there's some questions for you in the chat. I'm going to refer you to their DKG asked a couple of things and was also referred to your paper. And then I see we have Hannes, or actually Benjamin, I guess, is ahead of him. We'll have Benjamin go, and we're going to have to switch pretty quick to Kyle's. So let's make it quick. Go ahead, Benjamin.
Hi. So you said this worked for 8 of the devices. What happened with the other 16?
So what happened with those devices was that they would either not send us a TLS alert at all, or they would send the same TLS alert. So it means that we need to find some other channel to study that difference, because the certificate validation would be different in the both 2 cases, but the alerts are not necessary to be sent. I should also mention that the TLS protocol does not mandate the sending of these alerts.
Thanks, Hannes. Can you go quick?
Yeah, sure. Thanks for doing the work. I was wondering what type of devices those were. Did you sort of analyze whether those were sort of high-end IoT devices, like with A-class processors, or more these low-end devices, which obviously have different constraints?
They were all popular consumer devices, so pretty high-end, I would say. And I have a slide in the slide deck which has a list of all these devices, but they were like Alexa and smart TVs and Samsung Fridge.
Okay, so it's most likely running Linux, off-the-shelf Linux. Okay. Mm-hmm.
Cool. Thanks so much, Taha, for bringing that to us. Follow up in the chat with him if you would like. Bringing up Kyle's slides now, and we'll finish up with our last presentation where Kyle will be sharing with us performance measurements with video conferencing apps. Go ahead, Kyle. You got at least 10 minutes.
Great. Thanks, Dave. Yeah, so my name is Kyle. I'm a second-year PhD student at the University of Chicago, and today I'll be presenting our IMC paper measuring the performance and network utilization of popular video conferencing applications. And I want to start off by giving a little bit of motivation for this work, which actually came from a question that our local city officials here in Chicago asked us towards the beginning of the pandemic, namely, what is the baseline level of internet performance needed to support common video conferencing applications for remote learning? Now, this question is becoming increasingly relevant as local policymakers work to provide sufficient internet access to its citizens. So to answer this question, we've conducted a series of experiments to better understand both the requirements of VCAs and the causes of poor performance. So in this talk, I want to briefly highlight some of the core findings from each of the sections of our paper. And to start, in this work, we study 3 of the most popular VCAs in use right now: Zoom, Google Meet, and Microsoft Teams. So we start by determining what the bandwidth requirements are for a 2-person call on each of the VCAs, and find that Meet and Zoom use under 1 megabit per second on average in both directions, while Teams uses 1.4 and 1.86 megabits per second in the upstream and downstream directions, respectively. Now, for context, home internet users have access to speeds of up to 1 gigabit per second, and many subscribe to plans in the tens and hundreds of megabits per second. Additionally, the Federal Communications Commission, known as the FCC, defines broadband internet as 25 megabits down and 3 megabits up. Now, while there's still some debate over this definition, the actual utilization rates that we found for these apps that many consider to be pretty big bandwidth hogs are actually relatively low. But while utilization rates may be low, insufficient bandwidth is not the only cause of poor performance. Home internet connections can be dynamic and encounter interruptions in connectivity. So in this next part, we study how VCAs respond to these sorts of temporary disruptions. And to do so, we use the following setup, where we start a call on V1, which is a standard consumer laptop, and adjust the bandwidth capacity available to V1 at the router in order to simulate an interruption. Our experiment proceeds by starting the call under what are effectively unconstrained network conditions, and then 1 minute after starting, we reduce the available capacity to 1 megabit per second or less for 30 seconds. After this 30-second period, we revert to the original unconstrained network settings and allow the call to continue for another 3.5 minutes before ending it. Among our results, we find that VCAs can take quite a long time to recover from interruptions. In this figure, we measure the time to recovery, which we define as the time between when the interruption ends and when the median utilization returns to the median utilization from before the interruption. The levels on the x-axis indicate the available uplink capacity during the 30-second interruption. And while Zoom and Meet are usually faster than Teams to recover from drops to 0.75 and 1 megabit per second, all 3 VCAs can take over 25 seconds to recover from the most severe interruptions. These long recovery times may lead to poor performance, especially on networks that are prone to these types of interruptions. But interruptions aren't the only cause of dynamic network conditions. So in this next part, we study how the VCAs respond to competing traffic. And this is really important because there are often more than one user on a single network. And these other users could be hosting their own video conferencing calls or using streaming services like YouTube and Netflix. So to test how VCAs interact with other applications on a constrained network, we use the following setup, where we run a video conferencing call on V1 and initiate a competing application on C1. Both V1 and C1 are connected to the same network and will share the same bottleneck link. Again, we're setting the capacity available to V1 and C1 at the router. In each experiment, we start by reducing the capacity available to V1 and C1 before we've started either of the applications. Then we initiate a call on V1, wait 30 seconds, and then start the competing application on C1. Now, it might not surprise you to learn that applications aren't always fair with other types of applications, but we actually found that the VCAs are not always fair with themselves. So in this figure, we plot the upstream utilization over time for 2 different Teams calls using the same 3 megabit per second uplink. The gray region indicates the time period in which the 2 calls compete. The purple trend line is the utilization for the incumbent call running on V1, whereas the black trend line is the utilization for the competing call running on C1. And throughout the duration of the experiment, we find that the incumbent Teams call has a significantly higher average utilization than the competing call. Now, this lack of coordination between the calls has obviously implications on fairness and could mean that one competing VCA call could use more of the available bandwidth just because it started first. Now, up until this point, I've only discussed utilization and performance in 2-person calls, but as we all know, there are many different ways that people use VCAs. So in this next part, we explore how varying the number of participants and how people view the call affects utilization. We use the following setup for the experiments, in which all participants join the same VCA call. We consider 2 viewing modes, gallery and speaker mode. In gallery mode, you see everyone's video on the screen at once. This works by shrinking the size of each person's video. And in speaker mode, all participants enlarge participant A's video, streaming it at a high resolution. And what we find is that your utilization can be affected by how other participants use the VCA. In this figure, we show user A's uplink bitrate, or uplink utilization, when all other participants have user A's video enlarged. In most VCAs, this is when you pin a specific participant's video to the screen. And we show how the uplink utilization changes as we increase the total number of participants in the call. What we see is that as the number of participants increases, the utilization for Meet and Zoom remains relatively constant. But when using Teams, user A's uplink bitrate tends to increase with the number of participants. And this is a really realistic scenario. You can imagine it occurring during remote learning when all of the students have pinned their teacher's video to their screens. So understanding this behavior is really important when drafting broadband policy, especially given that the uplink Teams utilization approaches the FCC standard for broadband internet at 3 megabits per second when there are 8 participants in the call. So to recap, in our study of VCAs, we have several interesting findings that can inform policymakers that are designing internet provisioning legislation, namely that VCAs have relatively low utilization, that they can take quite a long time to recover from certain interruptions, that VCAs may not compete fairly, even among themselves, and finally, that how other people view the call can affect your utilization. I hope you've enjoyed this presentation. I'm happy to take any questions. You can email me at my last name, mcmillan@uchicago.edu. I know we're running a little low on time here.
Hi, Kyle. Thanks. This is Dave. We've got 2 people in the queue with a question or comment for you, and there's a couple more in the chat if you want to pick them up there. Otherwise, they'll do as you said. Go ahead, Andrew.
Hi, thank you, and thanks for the interesting presentation. It was mostly fascinating, so good to see. Just 2 quick questions. When you did this testing, did you consider or did you look at any differences between using a native app versus a browser client? And also, did you look at any differences from different device types to see if that made any material impact on this? Thank you.
Yeah, thanks for your question. So we actually looked at how, well, Google Meet, I guess the native application would be Google Chrome, so that's what we used the whole time. But we also looked at how Microsoft Teams performs in browsers. So For that part, we look at how utilization changes as you adjust the network settings, but also how certain QoE metrics change under different network settings. So stuff like freezes and quantization parameter. And then as for device type, we did most of our experiments on this Dell laptop that was running Ubuntu, but we also replicated some of the experiments on a Mac computer. But in case you were asking about like mobile devices or something, we were only looking at laptops.
Yeah, I was thinking more different processors, so with an i3 versus i9 type distinction, but maybe a discussion offline. Thank you.
Okay, sounds good.
Thanks a lot. Ali, why don't you go and then we'll wrap it up.
I suppose
we can hear you.
Yep. Right. Thanks for the talk. My question was when you were doing the video comparison, the video bitrate between Teams versus another Teams client or another competing client, were you double checking that you were actually capturing a similar video? Because a talking head versus moving body or moving head, I mean, makes a difference in terms of video bitrate, right? So I just want to make sure that you guys were conforming to using pretty much the same video for each webcam, so that it will be a fairer comparison.
Sure. Yeah. No, that's a really good point, and we did. So we had a pre-recorded talking head video that we used for all of the experiments.
Okay. All right. Thank you.
Yep.
Great. Thanks so much for joining us, Kyle. And thanks to the other contributors. Those were great talks. You can go find their papers and another recording of the presentation for the three of them are from IMC there. Thanks to Miria for helping put together the agenda again. I hope you all have a good week. And thanks lastly to Teresa Enghart for taking the minutes for us. And we will see you at the next meeting. Bye-bye.
And thanks to Dave. Bye.